Now let's see what happens when we turn on hydrogen bonding. Now we're expecting that hydrogen bonding, because it's a really sticky force, is going to help keep our liquid or gas or whatever together. So it's going to keep it condensed for a lot longer. Now, if we look at just a case where we can't have any hydrogen bonding. So we have tin, germanium, silicon, and carbon. None of those are a magic 4 atom. We have the same structure for all of these though. Notice that all of these are in the same column. We have 4 hydrogens stuck on each of those. Tetrahedral, not polar. So we're going to expect the trend that matters most for that to be molecular mass. Because as we get to bigger masses, each of these atoms end up being more polarizable, which means that it's easier to tug the electron around and induce the dipole and stick to its neighbor. So as we get heavier and heavier, it boils hotter and hotter. Now let's look at the same sort of trend for things in oxygen's column. Tellurium, selenium, sulfur, all of those are following the same sort of trend, and notice the slopes are even about the same. So when it's mostly the increase in a row making something more polarizable, we're seeing the same sort of increases or decreases in boiling points. But what happens when we actually have one of the magic 3 atoms, oxygen? All of a sudden, because it's so small and so good at having its electronegativity tug on the electrons of the hydrogen, all of a sudden, boiling point jumped up dramatically. If we are following this trend, we are probably expecting water to be boiling somewhere right around negative 80 degrees Celsius instead of positive 100 degrees Celsius. And we know that that's not where water boils. Now, what if that's just a weird quirk of water itself? I'm insisting that it's because it's one of these magic 3 atoms that I like to refer to them as. So let's take a look at a table that shows all of those trends. And actually, let me go ahead and get rid of the ink for a second there. Here we are. So you can see here we have the same trend for carbon's group 4. Groups 5, 6, and 7 are the ones that have one of my quote-unquote magic atoms, oxygen, nitrogen, and fluorine. All of these have the same trend, and notice even kind of about the same slope, until all of a sudden you jump to one of those magic 3. This is where we are predicting water to be, just like I did a second ago, extrapolating back from that slope and saying, yeah, water must boil at like negative 80. But water boils at 100. If we did the same sort of thing for hydrogen fluoride, we'd say, it probably boils at like a negative 100, maybe 110 Celsius. But no, it boils at about what, positive 10, positive 15? How about ammonia? Ammonia we are probably predicting was going to be boiling at negative 130, but it's boiling at only negative 35 or 40, something like that. So yeah, switching to these very small, highly electronegative atoms really, really cranks up the intermolecular attraction that it has to its neighbor. And so it really dramatically increased the boiling point. It stayed stuck to its neighbor for a lot longer.